Hey everybody, Trey here. Welcome to another episode in this Skew-T and Hodograph series. My apologies for the delay. I was a little bit under the weather last week, no pun intended, but feeling better now. And during that time, I was able to start gathering the information for the remaining videos in this series. Going to be a jam-packed conclusion to this series, starting with today's video. In the last video, we discussed how to estimate certain quantities from a hodograph. And now we're going to talk about applying what we've learned so far about hodographs. We're going to start today in this video with looking at common characteristics of hodographs that you might see when you are making a forecast. And then in the following videos, we're going to take a look at some hodographs for common environments. Just like we did with the Skew-Ts, we looked at different Skew-Ts for common environments. We're going to do the same thing for hodographs in the upcoming videos. But again, today we're going to talk about some common characteristics of hodographs that are often you'll see when you are analyzing hodographs to make a forecast. So let's get started. And I got a lot of this information from Cameron Nixon's just incredible research article called The Storm Relative Hodograph. The link is up here at the top of the page, but this article is one of the best research articles I've ever seen on hodographs. And I urge you to take a look at this if you want to go into a deeper dive about what we're going to talk about today and in the next few videos. Just an incredible article. So if you have a chance, please check this out. And I did kind of model what we're going to talk about today off of what Cameron talked about in this article. So again, if you want a deeper dive into what we're talking about today, go ahead and take a look at that article. The first thing we're going to talk about in this video is how the upper level storm relative winds play a role in supercell characteristics. And when we talk about upper level winds, we're talking about the layer between 6 and 12 kilometers above ground level. So we're talking about those winds at the highest portion of the atmosphere, the upper levels of the storm's reach. And again, just a quick review on storm relative. When we're talking about storm relative winds, we're taking out the storm motion. So when we say storm relative winds, we're talking about the winds that the storm feels itself. And just a refresher on how to figure out the storm relative winds, we start with our bunker's right mover storm motion here on our hodograph. And then we draw a vector back to the point on the hodograph that we are most interested in. So if we wanted to find the storm relative winds at the surface, we would start from the bunker's right mover storm motion, draw a vector back to the point on the hodograph that is associated with the surface, and that would be our storm relative wind vector. So when we're talking about weak storm relative winds in the upper levels, we're talking about storm relative winds that are generally less than 20 knots. And that might be a little bit difficult to ascertain just by looking at this. And in his article, Cameron describes a technique to kind of make this a storm relative hodograph where you subtract out the storm motion and then you rotate the hodograph in the direction of the storm motion. That's an excellent technique for analysis. It can be a little bit difficult sometimes to do so when you're just making a forecast and you just have hodographs that you're looking at online. So it can take a little bit of practice, but we want to be looking at this hodograph in a storm relative sense. So we want to base everything off of this bunker's right mover storm motion. So when we're talking about our upper level storm relative winds, let's go to the 6 kilometer point here. So let's draw our storm relative wind vector back to the 6 kilometer point here. Well, you notice that this vector is pretty small, and let's do say 8 kilometers here. Very much the same thing. So in this situation here, in this example hodograph, these storm relative winds are very weak above 6 kilometers. And what that means, generally when the upper level storm relative winds are less than 20 knots, less than or equal to 20 knots, we tend to have more of a high precipitation or HP storm mode. So the upper level storm relative winds control how much the precipitation is vented away from the mesocyclone. So when we talk about a weak storm relative wind situation in the upper levels, the precipitation is not able to be vented off very well, and so that rain and hail will fall near in that updraft, very close to that updraft, and the storm will become high precipitation. So this example here comes from May 22nd, 2016. We had a couple tornadoes in the southeast Texas panhandle, including this one near Memphis, Texas. And you can see here, based on what we saw with that hodograph, you'll notice that this tornado is very much wrapped in quite a bit of precipitation here. You can see the rain curtains there wrapping around this tornado. Well, that's because the upper level storm relative winds were pretty weak on that day, so the mesocyclone often became shrouded in precipitation. The tornadoes were a little bit difficult to view, and that is typical for these weak upper level wind scenarios. Now, when we're talking about strong upper level storm relative winds, we're generally considering winds that are greater than or equal to 40 knots in the 6 to 12 kilometer layer. So unlike our case where we had pretty weak storm relative winds in the upper levels of the atmosphere, again, if you transpose these vectors down to the axis, you'll see that these are much less than the 20 knot range ring here. So in this case, we would see an HP, high precipitation storm mode, whereas in this case, if we draw our storm relative wind vectors, here's our bunkers right storm motion. Let's go to 6 kilometers here. You'll notice that these wind vectors are much, much longer, have much greater magnitude than our first case that we looked at. Again, if we transpose these to the axis, you'll note that these are much greater than the 20 knot range ring, and even approaching the 40 knot range ring or more. And if we have cases like this, again, we have an LP or low precipitation storm mode. And that hodograph on the previous slide was associated with this storm near Roswell, New Mexico back in 2014. You can see here that the precipitation, this isn't the best example of a low precipitation supercell, but you'll notice that this precipitation is kind of shunted off to the northeast in the direction of those upper level winds, and you get this nice sculpted kind of updraft that is pretty much precipitation free. And that's what you'll get with strong upper level storm relative winds. So now we're going to talk about the mid-levels of the atmosphere, mid-level storm relative winds, and what role they play in supercell characteristics and what they look like on the hodograph. So when we talk about the mid-levels, we're going to come down a little bit from what we just talked about, and we're going to look at the 1 to 6 kilometer layer above ground level. So we're going to, for this portion, we're going to ignore the lowest levels of the atmosphere, and we're going to come down a little bit from what we just talked about, that 6 to 12 kilometer layer, and we're going to look at that middle portion of the atmosphere, that 1 to 6 kilometer layer. And the first thing we'll look at is the wind shear in the mid-levels. Of course, we've talked about wind shear quite a bit in this series. Wind shear is, again, the changing of the wind speed and direction with height. And the mid-level wind shear modulates how well the supercell characteristics can sustain themselves. So we'll call that supercell sustenance or maintenance. And when you have weak wind shear in the mid-levels, the hodograph will often look like this. You'll see the points here in that 1 to 6 kilometer layer pretty bunched up, and that just means that the winds are not really changing that much in both speed and direction in that layer. And when that's the case, when you have weak mid-level wind shear, you will have supercells that will tend to be more pulse type. They won't really sustain themselves for that long. They can still produce strong tornadoes, and you can still get supercells in weak mid-level shear environments, especially if you have strong low-level shear. But they'll often produce a tornado, and once that tornado dissipates, they'll often lose their rotation entirely and become non-severe and kind of multicellular. Now, when you have strong shear, in contrast, as we see here on the right, then we have supercells that, number one, kind of look more like supercells on radar. You'll see that classic sort of shape with that hook echo and the precipitation vented off in the direction of those winds aloft. And you'll have that supercell sustain itself for quite a while. You'll often see kind of more persistent, broad, rotating updrafts or mesocyclones. So in this case at the right, you can see we have pretty strong shear. If we start here at 1 kilometer, we'll draw our ground relative wind vectors here. And you'll notice that the winds are changing pretty drastically here in the mid-levels. We'll go up to 6 kilometers here. And you'll notice that we have quite a bit of shear in that 1 to 6 kilometer layer. So in that case, this was the infamous quad-state tornadic supercell from a couple of months ago in December. This was the 0Z Little Rock sounding from that night. And of course, we know that that supercell sustained itself for several hours over several states, produced multiple tornadoes, was a cyclic tornado producer. That's because, in part, because we had strong mid-level shear, that supercell was able to sustain itself for quite a while. Now we'll talk about the streamwise and crosswise nature of the mid-level winds. Now, we went pretty in-depth into the what streamwise and crosswise means in our previous video, part 7. So if you need a refresher on streamwise and crosswise vorticity, go ahead and go back to that video. I'll put a link in the description below. Just for a quick refresher, we're going to want to draw our storm relative wind vector, and then we draw our shear vector in the direction, which goes in the direction of the hodograph at a specific point. So we're doing this point kind of at the surface. And then our horizontal vorticity vector is always perpendicular and to the left, or outward from the hodograph, from the shear vector. So that is going to be our horizontal vorticity vector. So when our horizontal vorticity vector, or HVV, is parallel to the storm relative wind vector at a given level, then you have streamwise vorticity. When your horizontal vorticity vector is more perpendicular to the storm relative wind vector at a certain point, you have crosswise vorticity. And we said that the streamwise vorticity case is, especially in the low levels, is a lot more favorable for tornadic supercells. And we'll look at the nature of the mid-level winds here in terms of streamwise and crosswise. So let's take a look at this example here on the right. Let's say we'll go to 2 kilometers here, for example. So we draw our storm relative wind right there. Our shear vector goes along the hodograph in the direction of the hodograph, and our horizontal vorticity vector is always perpendicular and to the left of that. So you'll notice in this case, at 2 kilometers, we have almost perfectly streamwise winds here because our storm relative wind vector and our horizontal vorticity vector are pretty much perfectly parallel to one another. We can do the same thing here. Let's go to 5 kilometers. Still in that mid-level layer, that 1 to 6 kilometer layer. So there's our storm relative wind vector, our shear vector along the hodograph here, and the horizontal vorticity vector goes perpendicular and to the left of that shear vector. And you'll notice we have a significant streamwise component here at 5 kilometers because, again, our storm relative wind vector and our horizontal vorticity vector are pretty parallel to each other. So when this is the case, when you have an abundance of streamwise mid-level winds, so they're parallel to that horizontal vorticity vector, then you have an updraft that rotates as a whole. So when you have streamwise mid-level winds, the updraft as a whole will rotate. So you'll see signs of broad rotation. If you looked up at the storm, you'll see the whole storm rotating when you have streamwise mid-level winds. And often in these streamwise profiles, you'll often get these mothership kind of structures, and these streamwise profiles are much more conducive to really amazing storm structure. Now, when you have crosswise winds in the mid-levels, as we see here in the hodograph at right, when you have crosswise mid-level winds, the updraft does not rotate as a whole. So instead, you get rotation on the flanks of the updraft. So if we have our updraft here, we'll say, the whole updraft will not rotate as in the streamwise mid-level wind case, but you'll get rotation on the flanks of the updrafts. Often you'll get anticyclonic rotation on the left flank and cyclonic rotation on the right flank. And you can still get strong, significant tornadoes out of these. As we saw in this case here, this was the November 16th, 2015 tornado outbreak in the Texas Panhandle. You'll notice that we had a significant crosswise contribution to the winds in the mid-level. So let's go here at 4 kilometers. We'll just pick a point here. Draw our storm relative wind vector, our wind shear vector along the hodograph, and then our horizontal vorticity vector perpendicular and to the left of that shear vector. And you'll notice here the storm relative wind vector and the horizontal vorticity vector are very much perpendicular to each other. So we had a lot of crosswise mid-level winds. So we didn't get storms that night that rotated as a whole. We got strong rotation on the flanks of the storms, and as a result, you'll see in an upcoming picture here, I reuse this example. And this happens often in these crosswise mid-level wind cases. You'll see that the updrafts don't quite look as supercellular, so to speak. They are often quite tilted, or they might look more linear in nature. But you'll see that on the flanks, you'll see strong rotation on the flanks of the storms, and you can get strong tornadoes on those flanks. And we'll take a look at an image from that night in a few slides here to kind of give you a visual of that. So again, streamwise mid-level winds, the updraft rotates as a whole. Crosswise mid-level winds, the updraft does not rotate as a whole, instead rotates only on the flanks. So now we're going to talk about veering and backing of the winds with height and how they pertain to the hodograph. So veering winds with height are winds that turn in a clockwise direction with height. So if you had a surface wind in blue here out of the south, and you had a wind at 1 kilometer above ground level that was out of the southwest, you would have veering winds in that layer because the winds are turning in a clockwise direction with height. Backing, on the other hand, is winds that turn in a counterclockwise direction with height. So again, let's say we have southerly winds at the surface. Of course, winds are described by the direction that they're coming from, not the direction they're going to. So you have southerly winds at the surface, but let's say at 1 kilometer above that, the winds are out of the southeast or southeasterly. Well, then you would have backing winds because your winds are turning in a counterclockwise direction with height. So veering and backing also determine the type of advection that a certain layer is experiencing. Of course, advection is just the transport of air from one place to another, air or some other meteorological quantity. It's the transport of something from one place to another. So when you have veering winds in a certain layer, you have warm air advection. So warm air is being transported from a region into that region based on a clockwise turning wind profile with height in a certain layer. If you have backing winds in a certain layer, you have cold air advection. So not super pertinent to this particular discussion, but we may come back to these advection regimes and veering and backing later on in a subsequent video. So let's take a look at some examples here. So this hodograph here at right shows a generally veering wind profile with height. So as you can see here, the winds are generally turning in a clockwise direction with height, pretty much through the entire hodograph here. This is kind of an extreme example. When you have this kind of extreme example here where the winds are veering with height, here's our bunker's right mover storm motion. If the winds curve back, generally, if you were to draw a line from the surface through the bunker's right motion and continue on, notice how the hodograph continues past that line. And one of the kind of rough tools that we can use when assessing kind of storm characteristics just by looking at hodographs is that the storm presentation on radar is going to look pretty similar to the hodograph. So if we take a look here, this hodograph here translates to what we saw here. This was April 28th, 2014. The Louisville, Mississippi tornadic supercell produced this pretty violent tornado here as pictured on the right. But let's take this hodograph here. Let's transpose it on the supercell, on the radar image here at right. Let me turn the opacity down a little bit. So you can see the radar there in the background and the hodograph on top. And you'll notice here that the precipitation pattern, as shown on radar, pretty much follows the hodograph. You can see here's our tornado. The precipitation curves back around, and because that hodograph curves all the way back around, that precipitation is vented out ahead of the ongoing tornado. So when we have a situation like this, significant veering through the profile, you often will see a more, not high precipitation storm mode, but a tornado that will be more difficult to spot because that tornado is moving into the storm's own forward flank precipitation core. You can kind of see that from this image at the right. Number one, you can see kind of a lot of precipitation wrapping around this tornado, but you can also see in the direction of motion, it's moving this way. This is the forward flank precipitation core. So unless you were just to the south or southeast of it or in the inflow notch, which this chaser here, a friend of mine, Stephen Jones, was in that location, you wouldn't be able to see it very well. It would be shrouded by precipitation because it's moving into its own forward flank precipitation core. Now, on the other hand, let's go ahead and go to a backing regime. So we can have backing in a hodograph as well. And you can see here, we have kind of both of these regimes here. Some veering in the low levels, clockwise curvature in the low levels. But then it starts to back here in the mid levels. And this is, you may have heard of the often dreaded veer-back-veer or veer-back profile, where you have low-level veering of the hodograph, veering of the winds, and then in the mid-levels it backs once again. Now, there's a lot of negative sort of connotations with veer-back-veer. It can create a messy storm mode, etc. And it can, maybe wreak havoc on supercell maintenance. But while those can be true, and we'll talk about those maybe in a second here, when you have a hodograph that veers in the low levels and then backs, so here's our storm motion vector here, you'll notice that the winds, the mid-level winds back a little bit. Well, what that's going to do is it's going to allow that precipitation to be vented away from the low-level mesocyclone. So storm spotting becomes a lot easier. If there's a tornado, it's not going to be shrouded in precipitation because it's not moving into its own forward flank precipitation core. So this was the November 16th, 2015 Texas Panhandle outbreak. And we'll do the same thing as we did on the last example. We'll try to transpose the hodograph here on top of the radar image. So radar image here at left. I'm going to make this a little bit smaller so it can kind of translate here. We'll look at this northern supercell. So you'll notice here that once again the hodograph pretty well follows the precipitation pattern here on radar pretty well follows the hodograph. So we've got our tornado here. The precipitation wraps around there. But because we have this backing aloft, that precipitation aloft is vented well away from the tornado cyclone here. So given the storm motion, the tornado is not moving into its own forward flank precipitation core. And you can see here in this photo at the right, a couple things. Number one, we talked about this example previously when we talked about crosswise mid-level winds. And this was the case on this event. And if you were to take away the bottom of this image, you didn't know there was a tornado ongoing, you'd think, wow, that doesn't look like a very potent thunderstorm. It looks like just a normal monsoon thunderstorm maybe. But you'll notice this flank here, very much tilted, and that was associated with that mesocyclone and that tornado. So again, with crosswise mid-level winds, only the flanks of the storm rotate. You wouldn't be able to see a lot of broad rotation if you were to just look at this storm. But if you look closely, you can see that flank here, that right flank, was able to rotate pretty intensely and produce multiple tornadoes. Second thing we can see here is that, again, because we have a little bit of backing in the mid-levels, the precipitation is vented well away from the tornado cyclone. So we have our very visible tornado here, not shrouded in rain, and all that precipitation is vented well off, in this case, to the northeast. So storm spotting on this night was pretty good. There was enough lightning so you could see the tornadoes, and the tornadoes were not shrouded in rain because they were not moving into their own forward flank precipitation core. You can see the same thing here with this southern supercell. Tornado was here, and all that precipitation vented off to the northeast away from that tornado cyclone. So storm spotting becomes a lot easier when you have a little bit of backing in the mid-level. So backing does play a role in kind of storm characteristics. Veer-back a veer-back profile is not always a bad thing. Now, of course, if we have, let's say we have our storm motion here, and our hodograph goes something like this, if we do have enough backing to where we have a situation like we saw with the Louisville tornado where you have all that veering and then it backs back like that in the mid-levels, then you may have some trouble spotting the tornadoes because, again, the tornado will be moving into the forward flank precipitation core. But in cases like this, often a little bit of backing in the mid-levels is not a bad thing because it vents that precipitation well away from the tornado cyclone. One last comment on the veer-back profile. There's some research that has stated that the smaller the inflection point is to where the winds start to back, and the higher up it is in the profile, the less implications it has on supercell characteristics and maintenance. So in this case on the right here, we have large curvature in the low levels, which is favorable for right-moving supercells. And we have this inflection point here at about 3 kilometers. The winds start to back here. Well, pretty small inflection point for one, and two, it's located outside of the effective inflow layer. And we talked about the effective inflow layer in a previous video. And the effective inflow layer is just, you lift a bunch of parcels from the surface, and until they run out of buoyancy, they will continue to rise. And that point where they start to run out of buoyancy, they don't meet that certain threshold for buoyancy, that area below that point is the effective inflow layer. So in this case, on any hodograph, it's denoted by these blue lines here. So that is your effective inflow layer. It goes up to about 2.5 kilometers. And I found that if the inflection point is above that effective inflow layer, and the higher up it is above that effective inflow layer, the less influence it has on supercell characteristics and supercell maintenance. So something to keep in mind when we're looking at these kind of veer-back wind profiles that have gotten so much kind of negative connotations associated with them. Not always a bad thing to have some backing in the mid-levels, as it vents that precipitation away from the mesocyclone and allows for, number one, really good storm spotting. If there's a tornado, you'll be able to see it. Number two, it allows that mesocyclone to maintain itself perhaps a little bit longer because it's not running into that forward flank precipitation region as we saw in our Louisville, Mississippi example. So that's all I've got for this video. Hope you enjoyed it. Hope you learned something. And in the next video, we'll take a look at a bunch of different hodographs for different environments. Just like we did with the Skew-Ts, we'll look at some common hodographs you might see for different regimes and how they might impact what severe hazards you might see and what supercell characteristics you might see as well. So that's all for now. Thanks for watching, and we will see you in the next video.